Perth Linux Users Group, talking Linux and open source.
Thanks everyone for coming to Plug. This is the June talk about the square kilometre array and how it will work, if you couldn't read that earlier. I will hand this off to Ken Vinsen, who's got a very interesting talk for us tonight. So thanks for coming and hope you enjoy.
Is that how it will work or how it does work?
Will, because we're building it. Right. For those of you who don't know how I tend to do these things, you ain't going to sit there just absorbing things. You're going to have to do some mental maths. It's actually really simple. Most of the mental maths, you can do it on two hands. So, you know, if any of you struggle to count above 10, you should be from Norfolk like me, where we have 11 fingers, and it can be quite handy. And for those of you who get embarrassed by making mistakes with mental maths, I persecute wickedly. Now, fortunately, it's a small venue, and my hearing aids have packed in. So if I sort of move and look at you, it's because I'm lip reading. Oh.
Starts like this. Space, it says, is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the street to the chemist, but that's just peanuts to space. Listen, and so on.
That's the introduction to the Hitchhiker's Guide to the Galaxy. Should be compulsory reading to all year 10s who want to go into STEM. Because not only is it funny, it's actually accurate. So, as I said, some thinking. And what you can win is a mug that will show you the galactic core when you put a hot beverage in it. In Sheldon talk. All right. Now, we're building the biggest science instrument the world has seen. Now, if I took a day's recordings and put it on my 64 gig iPhone, how many years do you think you would be listening to the playback and will work in units of millions of years? And you can do it with one hand. Pardon? It's just a data stream coming through. We're not worried about that. It's a measurement set which you've never heard of.
If I'm storing my stuff in FAC, it's going to
You wouldn't know what a measurement set is, because that's what we use.
I'm going to say 100 million.
You can do it on one hand.
4 million.
There's one number left. Who said 2 million? Yeah, well, it works. That's why I tend to try to keep the numbers to 5, because otherwise it can take a long, long time. So we're talking about 2 million years of this type of data. Now, one of the things we have to remember is it turns out that astronomy is actually weirder than fiction. I'm sure you all recognize Tatooine. 2 suns. I mean, it sounds cool, doesn't it? But in astronomy over the last year, we've had some amazing results. Our nearest neighbor, Proxima Centauri, has a planet around it. Now, it's only 4.2 light years away, which really doesn't sound that much, does it? But at 40,113,497,203,472 kilometres, and 0.6 if we're really worrying, it is actually a damn long way away. But it's got 3 stars. So it's centred on a red dwarf here, which you can't see with your naked eye. It's too faint. You need a telescope. But it's also then got the Alpha Centauri binary pair. So you could be on this planet, watch this sun come down. Now, these 2 rotate around each other, so they could rise and one of them set at the same time as the other one comes back up again. George Lucas, come on, guy. Reality is much better at coming up with really weird stuff. Now, for those of you who... Pardon?
I told you randomness was important.
For those of you who have seen in the paper, I've been working with Dalkeith Primary School, and we're going to send messages here. We've talked the European Space Agency into lending us new Nausea, and I'm going to be pointing the dish there, and we're going to be saying, hello from planet Earth, or words to that effect. Now, just to sort of emphasize how far away it is, the fastest man-made raft is Helios 2. It's a solar probe that hit the sun at 250,000 kilometers an hour. It would still take 18,000 years to get there. So human generation every 35 years, do the maths. It's going to take a damn long time to get there, and you really have to get on with people to be able to live that long. We also found gravity waves. We've been looking for 100 years for these suckers. And we finally found one last year. And we've actually found another 2 since. These 2 black holes, one's 36 times the mass of our sun, and the other is 29 times the mass of our sun. But we have to remember, those waves and ripples are going through you right now. But we're talking about movements of sort of half the width of a proton. It's really very small. And then, of course, TRAPPIST, 40 light years away, 7 rocky planets, 3 in the actual Goldilocks zone. Do you want to actually see what Kepler brought back? This is it. This is actually the real image from Kepler, of TRAPPIST-1. And what you're looking at is tiny changes inside here that we work this out from. All right, so let's just quickly restate our SI units, because most people are sort of familiar up to about here, but we've also got to move down here. And for later on, remember that number there, the volume of the water on the planet. I mean, we're talking zetaliters. That's an awful lot of water. So, in one slide, what is the SKA? It's going to be built in 2 phases. Phase 1 is what we're designing now. Critical design review for it is due next year. Tender will then start later in that year to actually build. 2 components to it, one here in Australia, one in South Africa. We've got the low frequency, so we'll be putting 130,000 dipoles on the ground out in the Murchison. There are 3 host countries. 2 of them have actually got telescopes, and 1 is where the HQ is based. Now, we, as a community, are actually pretty livid. The Italians offered us a castle in Tuscany to be the HQ. I mean, how cool is that? But the Brits said, well, we've put 110 million in, we're going to Manchester. Oh. So it's going to Jodrell Bank, unfortunately, which is nowhere near as cool and quaint as Tuscany, but well, such is life. There are currently 10 members to the consortia. Us, the Canadians, Chinese, Indians, Kiwis, Italians, South Africans, Swedes, the Dutch, and the Brits. 10 work packages. Australia is involved in all of them, apart from infrastructure, South Africa. We actually are heavily involved in every component of this. Total cost cap for phase 1 is 650 million euros, which is about 1.2 billion Australian dollars. It has been downsized twice already because when we did the estimates, the computing killed us every time. It's not the dishes, it's not the antennas, it's the computing. But they've also put a power cap on us of 5 megawatts, which is very hard to achieve. Some of the requirements that we've actually got. So these are the real requirements now that we're at this point. We'll be having, coming into the main supercomputer, 7,400 gigabit Ethernet connections, 5,800 gigabit connections. We have to be able to store 12 hours worth of data. That means around 5 petabytes of memory. Now, that may change later this week, because 5 petabytes of memory is expensive. So we might actually be changing that, and it will be going to disk, and we'll deal with it later. But of course, all we're actually doing is postponing the problem of we still have to deal with all this data, no matter what. For the archivists among you, we have to keep the data for 50 years. Tape is not dead, long live tape. I know, but if you recycle and keep you're going to have to do it, because this is a real requirement on us, because what we record now, our grandchildren may well be looking at. So they need to be able to see it. Now, glass plates were easy. You just put them in a filing cabinet and left them there. But we're talking a whole different scale of data. We'll be looking initially at about 34 petabytes for mid and 11 petabytes for low, going down to this long-term storage, which is a challenge. We also have to be able to deliver within 10 minutes or start delivering data up to a petabyte a day, which is an awful lot of data when all said and done. And it's really quite nice that the new cable is going into Singapore, which part of it is on the back of what we need to be able to do this thing, because otherwise we'd never do that. You want?
What did the universe look like when the first galaxies formed?
What are gravitational waves? How does magnetism work throughout the universe?
Come si formano i pianeti?
How many gravitational waves are passing through me right now?
What is dark matter?
What is the impact of magnetic fields on the formation of galaxies?
宇宙の歴史はどうなったか。¿Estaba Einstein en lo correcto?
And for me, the most important is there life out there?
We ask ourselves, what is the most useful thing that a radio telescope can contribute to the answer to these big questions? We are building a time machine. We're looking at what our surroundings were like almost at their inception. The question is, how are we actually going to make this happen?
We're building what will be the largest science facility ever built by mankind.
To be able to achieve the scientific goals that we wanted to be able to achieve, we need to create a machine which is less a telescope, it's almost more an IT machine.
We're pushing technology to its limits.
What we're talking about now is two telescopes.
Our site is in the middle of the Western Australian desert.
Far away from towns, radio interference, anything that could impact on the science that we're trying to do. We've already started. We've got antennas at the site. We'll have hundreds of thousands more. It'll stretch out beyond the horizon.
We're building hundreds of dishes in a remote location in the middle of South Africa. And it's really tough. It's a hot environment.
Ha! Compared to us.
These dishes are going to spread out over literally hundreds of kilometers.
Een project als dit kan alleen tot stand komen als wetenschappers wereldwijd met elkaar samenwerken. We've got to get 500 engineers to work together over 20 countries in all time zones in the world.
It's like building a jigsaw puzzle, the pieces keep changing.
Part A being designed in one place fits to part B being designed literally on the other side of the world.
Every new telescope, there are always new discoveries, and they are never the discoveries you build a telescope for.
We're almost bound to discover something new, something that will disrupt our current everyday life.
That generates new knowledge now.
Huge amounts of data.
Imagine the amount of data that's flowing through the internet at any one moment. We're talking about that kind of level coming out steadily.
इतने सारे डेटा का सही मतलब निकालने के लिए नया सॉफ्टवेयर बनाना ही पड़ेगा. The SK can do for interplanetary exploration what broadband did for the internet.
We're doing this now. There's equipment on the ground in South Africa and Australia.
Radio waves gives us a unique way of probing the deep universe.
We can do all of this by picking up incredibly faint signals, radio waves coming from the dawn of the universe.
What we will discover is the unknown.
We're going to build the real thing. It's not just dreaming.
And there's stuff on the ground out there. We have terabytes of data, and I'll show you some real numbers of what we're putting into store every day. But this is where we're going to build it. The Shire of Murchison. It's 41,000 square kilometres. Population 102. Which gives it a population density of 2 million people per square kilometre. Now, to put that into some context for you, the Netherlands, the world, Australian capital cities, Alaska, Midwest WA, Greenland, Murchison. It really is very, very quiet out there, which is a fantastic thing for what we need to do, because we need real radio quiet. Now, how much radio quiet? It's always best to illustrate with an example. Everybody, feet firmly on the floor. Let's see if you can feel this. Nah, you feel it? Did the Earth move for you? Yes? No?
Every time.
Oh, well, yeah, but that's you and me, James. It's not really surprising because that was 60 microjoules of energy being imparted into the ground. Before 2014, in the 60 years of radio astronomy, that was more than all the radio telescopes had ever recorded. And then the MWA came online here in Australia, and in a year, doubled it. Then LOFAR came online and doubled that doubling. This year, ASCAP's coming online, which will double it again. And that's in 3 years. We've now got huge, huge data rates coming through. The Chinese will be bringing FAST online shortly. FAST is the 500-meter telescope they've built. If you get a chance, go and look it up on the internet and go and look at the time-lapse video of how you build a telescope with a dish that is 500 meters across. It's an astonishing piece of engineering. I mean, they don't have cut some corners, but by crikey. And the software is made by ICRA. We provide all the goodies that go into that. Now, you heard them talk about telescopes as a time machine. Light takes time to get to you. So as we zoom out on this young lady, distance increases and the time it takes slowly starts to increase. When we're dealing with sort of small units, it's not really noticeable. But let's move out. We start to get to seconds. Go out past Mars, and we're now talking 10 days.
There should be a factor of 3, shouldn't there? Like 3 times 10 to the 8.
On yeah. All right. I mean, and let's look at, to get to our galactic core. We're talking 30,000 years. We're 100,000 light years across. You know, I mean, 30,000 years ago, that's what the planets looked like. Neanderthals were around, and we find their remains. Australia was a interesting shape. Ice Age up the top there. But we can then go out to galaxies as well, where we're talking 30 million years ago. I mean, that's the Earth looked like roughly then. And you would want to meet this fella. This is a carnivorous kangaroo that lived here in Australia. It didn't hop, because you see it hasn't evolved the feet quite yet, but it was also a meat eater. You don't see many of them nowadays. Okay. For a prize. Now, one of the things that we're building about this thing is it is super sensitive. We will be able to detect an airport radar on a planet a certain distance away. Now, how many light years do you think? You can do it with 2 hands.
7,
8, 10.
Where was the 10? So it's 10 light years away to be able to see things. Now, I mean, that would be a great result because it means we're not alone. It also means that there will be more investment in science because people will get excited about it. Now, if we really want to get people into the STEM world, we need that planet to be full of dinosaurs. Space and dinosaurs is a killer combination for kids. Kids will come into science in their droves. Accountants will fade away, and there will no longer be that horrible red line through your budget saying, we can't afford this, justify this, because there won't be enough of them. Lawyers, the same thing, fade away, because everybody will be going into science, because it will be cool and exciting. But we've also got people like Elon Musk and Stephen Hawking arguing the fact that, do we really want them to know we're here? Because if it's a dinosaur planet, top dinosaurs were predators. So as long as I can run fast, oh, I'm all right, I can run faster than James. I can run faster than James. I'll be okay, because they're going to be coming and thinking, oh, look at this, a smorgasbord of food that self-regenerates. All right, so let's do a little bit of the sciencey thing. Optical light is actually a really narrow band. It's 390 to 750 nanometers. And that comes through our atmosphere. But that's what we've evolved to see, those frequencies. We can actually characterize that pretty well with three numbers. R, G, B. We use it all the time. The band for radio is a tad bigger. And that's where we start to hit a problem, because we need around 1.5 million channels to get decent frequency resolution at the kilohertz range when we're into megahertz here. And that means our file formats are stupidly big. Mostly, though, we're looking for this, hydrogen, H1. When the electron does a spin inversion, it emits a radio wave at 21 centimeters, and that's what we're looking for primarily. Now, after the Big Bang, only 4% of that aftermath is matter that we understand as matter, what makes us up. The rest of it was dark energy and dark matter. And we have no idea what those are. But of that 4%, 91% is hydrogen. So there is plenty of it out there. All right, now let's just quickly show you the difference between what the optical boys see and what the radio boys. This is M81 and M82. One of the vagaries of the human eye, we see dark things on a light background better than light on a dark. So let's just invert the image, because my money is most of you couldn't see NGC 3077. Now, when we look at this, we can see the stars here. These look isolated, don't they? Now, we have to remember that is 36,000 light years from side to side. Let's look at the hydrogen. And that tells us a very different story. These galaxies are interacting over hundreds of thousands of light years. Now, what we think happened with computer simulations, let me just overlay the images so they look good. M82 here got caught in M81's gravity well, came through here, slingshot around, ripped the heart out of NGC 3077, dropped bits and pieces as it went through, and it's about to come back in again. You'll notice there's clear bits in the middle there. One of the things we use for evidence to say, maybe this is black holes. Because I picked these deliberately because they're based on galaxies, so there's nothing much in between. And we don't see a huge amount in there. So this is probably an accretion disk that's spinning and nothing's getting out of there. But we can also see molecules. So water, kind of handy. It's what we are mostly. I mean, if I desiccated one of you, it would be a pile of dust on my hand. And that's it. It's really quite depressing when you get reduced down to that. That's all we are. Hydrogen sulfide, formaldehyde. But these two are interesting. Aminoacetylnitrile glycoaldehyde. That's a simple sugar. You'll find it in, or cousins to it, in trees in New Zealand. Because New Zealand separated from Pangaea before anybody else and never came back. So the trees there didn't need to evolve much. And it's really simple. This is a precursor to an amino acid. And it's just simple organic count. Now these two you'll find in the Sagittarius and Orion Nebula. So if you go out tonight and look at Orion, the sword, the second star down, it's a nebula. And these two are in there in such abundance that we can see them with the radio telescope. Now we need a big collecting area because our radio photons are WIMPs. That was built the same year I was born. It's the Parkes dish. It's still the best pulsar hunter on the planet, and it was built in 1961. How many pixels do you think it generates? 1. Well, actually it doesn't now. It generates 16 because we've now got phased array feeds in it here. But it used to just generate 1 pixel. All of that area just for 1 pixel. The other reason we need big dishes is a thing called resolution, or the angle that we're looking through here. Now, this is a real problem because the angular resolution that we need to worry about, because when light hits something, it becomes like a wave, and you get these ripple patterns. Now, with optical light, it's only in nanometers. Your eye pupil is 125 mils-ish, which means we can get an angular resolution of about an arc second. To do that in radio, we need a dish that's 53 kilometers across. Tad hard to build. So we used a different approach. We can't build a single dish to do that. So we use a thing called interferometry. So we use the fact that we know these fringes occur, and we know that the Earth rotates, and we know that we can time the signal when it arrives at one antenna to another antenna. We can actually correlate the signal. And this is why the stupid computing requirements are necessary, because we've got 130,000 antennas going out into the field. So there are two types of imaging. Direct imaging, which is cameras, optical telescopes, and single dish radio telescopes. And it's pretty much just like how your phone works. Cheese. But we can't do that. We have to use indirect imaging to be able to do this type of thing. And it's the same techniques that are used in PETs, ultrasounds, MRIs, nuclear magnetic resonance. All of these type of imaging techniques use this type of methodology as well. So, the Pan-STARRS gigapixel camera, 1.4 billion pixels that thing is. It's not bad. Produces some really nice images. If you go and look at the Skynet.org, which is a project of mine, I'm using images from this to do some citizen science work, but we can't use that type of approach. What we actually have to do is use aperture synthesis and interferometry. So the Earth rotates, and we sample the sky based on that, but we also sample based on the interference patterns. So we'll be doing an observation run for an hour to 8 hours. And all of that data is coming through, and we then have to correlate each of the images. Now, the Palsy Center is named after Joseph Palsy, who was the first person to build an interferometer, along with Ruby Payne Scott, and an Oxford guy called Martin Ryle. Now, Martin Ryle went on and got a Nobel Prize. Joseph was ignored. Ruby was fired because she had the audacity to get pregnant. And we're talking sort of the late 40s, early 50s. And at the time, the CSIRO model, thou shalt not get married, and she did, but kept it quiet. And then she unfortunately got pregnant. And once that showed, the poor lady was actually fired by it. But she did all the maths that we use for all of this. No, she died recently. When Brian Schmidt did her oratory, I mean, the poor guy was crying because he had to explain, how stupid were we?
It was standard practice.
Yeah, I know, but it's pretty stupid, as we see now. So what we see as the Earth rotates, what we get over time then is these interference patterns. And we can then slowly resolve them into the sources that we're looking at. And essentially that's what we're doing all the time. But the problem becomes a bit more complicated in that we then have to correlate all of the baselines. So if we've got a wave front coming in here, it will arrive here fractionally sooner than here. So we have to record all of that information, including the timing. And then we can correlate each of these. So with 4 dishes, we've got 6 baselines. We'll be building stations of antennas. So we're probably looking at tens of thousands. So this number gets extremely large. We have to do that using FPGA. ASCAP, which is 36 dishes, is used as an FPGA correlator, and at the moment it can't keep up. Everything is being looked at because we need grunt. For the MWA, we did it with GPUs. And so we have a GPU correlator on that one. But traditionally, I mean, FPGA is faster, it's lower power, And we've been building them for a long time, but it doesn't scale. And that's the problem. We'll talk about that one later. Once we've got that, we then have to do sort of the harder maths. So the output of the interferometry, we multiply all the pairs of signals together and we get a complex visibility, which has basically got amplitude and phase. We then do a Fourier transform of that and move it into the UV domain, and that then gives us the sky intensity distribution. And we have to do that across thousands of frequencies. And this is what we get from the correlator, and it's big. And we call it a measurement set, and that's the file format that we use for this. This is something that was specifically designed for astronomy. Astronomy data doesn't compress well because it's so noisy. There isn't that much regularity to it. So for each time interval, there is a value for each baseline pair. And that suddenly starts to get a huge problem. And that's what we'll be looking at with the MWA. James has just given me a load of data from Roy Hill, train movements past the observatory, so that I can try and see whether I can see the engines with the telescope. Because then if I can recognize it at certain times, I can mitigate that and remove that radio frequency interference from what we're seeing in the sky signal. So this is what happens. The antennas put it into the correlator. The science data processor really is the bit that does all the work. Now, the core components for that are being designed here in Perth by us. And then we go to a long-term archive. Now, that is going to be regional centers scattered around the world, very like the way the Large Hadron Collider works. So we have to move huge quantities of data all the time. Now, MWA at the moment is putting into its thing about 1.4 terabytes an hour, and we put down to disk about 5 petabytes a year. Sustained. That volume of data is also replicated to Brown University in the United States, Wellington, and to Pune. So part of the reason the internet going out to Singapore is so shy is that we've got big chunks of it doing our data. But when they like that fibre, things will get an awful lot better. ASCAP is coming online now. They have a little problem in the data coming in here is coming in too fast, and they need to work on that. But we're looking at 8 terabytes an hour of data coming into this, and they'll be putting about 5.5 petabytes a year to disk. We're starting to work, and finally, shouldn't say finally because this is on record, but the federal government have actually decided to fund us for the first time. Until now, we've been funded purely by the state. So thank you very much, everybody, as taxpayers. You kept us going. Finally, the feds have realised that us and ASCAT and the CSIRO guys actually do know what we're doing, and we're damn good at this. And to get us to the final parts of this, they're now funding the final part of this work for the next couple of years. Because SKA low adds a whole new problem to it. 1,800 terabytes an hour coming through onto this. And we'll be dumping data, we think, at about 150 petabytes a year. And then that is also going to be replicated out around the world, which is a bit of a challenge. Now, what the STP is actually doing is providing the final science-ready image. Because the time it takes to compute these things, we have to get that image to a point where it's ready to ship out. People can do further post-processing on it. That's up to them. If they've got their own supercomputer, cool. What we're looking at doing is getting it to the point where we can give out visibilities of all that data. We'll establish what the flux densities are in Jansky's, named after the guy who actually discovered that we do see signals coming in from space, which is Carl Jansky. We do all the gridding. We're actually looking at getting rid of these two steps with a whole new approach to doing this, which is really cool. I mean, some mathematicians at IBM in Zurich have come up with a really cool idea And we're working with them directly, and we're feeding data. It actually should have finished by now. We'll check later on. Moving the data so that we can send them raw voltages from MWA for them to start checking their algorithms. And then we do artifact removal via the point spread functions based on what we know about the telescope. Okay, so we need a bloody big computer. Now, core PCs is wrong. It should be cores. How many cores do you think we need to do this? And we'll work in units of 100 million. And you can do it with one hand.
This
one digit left. So we'll need about 100 million cores of compute to be able to do this for the final system. Now, let's put this into some context for you with stats from the Australian Bureau of Statistics. Every 6 months, they record all the internet traffic that we download. So to December 2016, we downloaded 2,587,056 terabytes. For SKA phase 1, and that's in 3 months, that's 3 months of data. SKA low will do that in 4 hours. But the whole of Australia, downloaded in 3 months, will be processing in 4 hours. At the STP, after it's been through various components, it's about 40 days. So basically, everything that goes through will be doing sort of a month and a bit to get that data crunched. So where are we at the moment? Well, the top supercomputer on the planet is Sunway in China, and it sits at about 10 million cores. Extrapolating, we're hopeful. This is definitely going to be doable. Now, this computer here is Tianhe-2, which was the Chinese supercomputer that preceded Sunway. Tianhe is Mandarin for galaxy, which is cool because we use it a lot. But they have a dirty secret. This is them at peak performance. They can't afford the power bill. So they don't actually run most of their cores. They actually have them turned off. So if we want to use them, we have to make sure that there are machines running. Now, we work with the Shanghai Observatory, and we get access to Tianhe-2 to do a lot of our experiments, because you might have heard me discussing the palsy situation over the next week, where they've just basically said everybody off, and we have 2 live telescopes. This isn't really how systems should be operated. And one of the issues with it, whereas the Chinese just say, yeah, sure, just give us a few weeks' notice, we'll turn it on. Well, in Shanghai, so it's okay. You know, it's a little way in from Shanghai. For, you know, it's 20 million people there. It's the same, nearly the same population as Australia. But the efficiency of our code is woeful. FFTs is our sort of primary thing. And here they are on 366 of the top supercomputers on the planet. One exception, that one there. Anyone want to make a guess what hardware that is? You can't buy it anymore. Yes, it's Sun's, Sun computers. Unfortunately, you can't buy them anymore. You know, it would have been fantastic for what we need. But something about the way they do their optimization, they can get 60% efficiency. All right, so how is this going to work? What we will have is an observation going into a buffer. Now, and again, I'll reiterate, this might have changed by the end of today. This buffer will record that data. Now, the idea is that this would be a memory buffer, because it's very expensive in time to write things to and from disk. So when that buffer's full, we then need to move it into a workflow, which will do all this scientific processing. Now, each of the astronomy projects has a different type of workflow. And we have to be very adaptive in here. At the same time, the second observation will be filling another buffer, because we'll be sucking that data over. When that observation's finished, we'll go to a second workflow, but this one needs to be finished. If it's not, the plan was to write to /dev/null. Yep. We can't do anything about it. We cannot process that data. We've got the next one coming in. Sorry guys, you're out of here. This data needs to be rescinded. But unfortunately, that is a huge amount of memory with a huge cost. So what they're now proposing is that this goes to disks. So we just have banks of disks that we fill up, but all we're doing is just moving the problem. You've still got to get it all back from disk to feed into here. But what they're relying on is the fact that we can theoretically observe 24/7, but we tend not to, because it's what people need to observe. And it depends what's in the sky and where the Earth is in its precession around the sun, and. So quite often, there'll be sort of 4 or 5 hour windows when nothing's happening. And the hope is that we can then get the data out. But it does put a hard line on, if we don't get that window, well, you can't do your observation, because we'll never be able to get the data down to disk and back again to be able to do this. We're not very happy with this solution, needless to say, but it's driven by our friends with red pens, because they're trying to save money, because it's already costing a significant part of the budget. Right, now the dishes will produce a huge amount of data. Now we're talking the global internet data. This was done by Cisco. You can do it with 2 hands. How many times the global internet traffic do you think?
9.
10. No, we've had 1, and we've had 2. So 1, 2, 10, 10. So it's. So how do we do this? What it comes down to is essentially the good old-fashioned divide and conquer problem. Now, 1 painter can paint a room in a day. 2 painters can paint it in half a day. Now, I deliberately picked this room, or this image for a room, because it's got fiddly bits. So how do we deal with that? Because you can't evenly distribute the work there. It is not a homogeneous system, and nor is astronomy. You cannot use homogeneous computing. So we could have a third specialist painter who sits over there. But then we have another problem. What happens if they all run out of paint at the same time and have to go back to the bucket at the same time? We hit a congestion problem. And we don't want that. So maybe we could use streaming painting, where we stream the data to them and use the same type of approach, where we're streaming all of that data through to do. And really, this is how we will do it, except for instead of 3, there will be hundreds of thousands to do this. Now, there isn't actually any software that can do this, because what we need is software that is deterministic. It has to run in a known time in that window. So we cannot have a loop that says while A is less than B, because we don't know when it's going to hit that limit. What we can have is for I in range 0 to 100, that's fine, because we can actually unroll that very easily. So what we've designed is this system called the Deluging Data Activated Flow Graph Engine. The Mandarin word for flow is Lu. Those 2 bits there mean water, rock, and moving around it. Chen is from Beijing. So we have this in there. So the idea we have is we want to do what is actually good practice within any organization. The guys who know about the hardware look after the hardware. You do not let the idiot users near that system. The last thing you want is idiot users going, oh, let's up me file limits. Oh, let's change this. Let's modify my swap space. They would be dangerous doing that. So they work at a logical level where they say, what we want to do is I want to do these types of fast Fourier transforms. I want to scatter it across frequencies by this amount. I want to do a clean process over 100 iterations. Now, we also need to be able to work out how long roughly that's going to take. So we also have to have resource analyzers sitting in there to be able to sort of check as we run these jobs and feed back how long did it take. Now that then needs to be translated into a template for a physical graph. When you're talking of hundreds of millions of cores, you can bet money, and big money, that some of them will be broken. Mean time to failure. So what we have to then do is say, this is roughly what we need to lay out. So it's very like how TensorFlow works, but deterministic. We can then deploy that physically to the hardware by asking, right, what's available, what's working, and then we actually run the job. And we also have this workload analyzer. Now, at the moment, this is using things like strace and some little utilities that I wrote that sit there looking at /proc and just polling and testing. Where are we doing? What are we doing? How are we going? We keep completely away from disk if we can. A lot of this work we do on Amazon because you can do what you damn well feel like. And we do. Amazon were actually very generous, and they came up with the Astrocomputing project. And we've effectively got about $60,000 worth of free compute from them to do these experiments. We've just about run out of money on this, and there's still a bit left, and we're the only project that's actually given the results and published, so Amazon like us. So they're now sort of saying, well, maybe we'll give you another 75,000, which is pretty cool. And what we do, we're working on a project called Chili's, which is being done by the Americans. And now, if you're sort of interested in this stuff, go and look up the Jansky lecture that Jacqueline gave, and you'll hear her refer to her friends in Australia. Because the project is actually run out of Columbia University in the United States. But they haven't got the grunt to do it. We have. So we do all of the imaging for these guys to do this. And we're actually prototyping this thing. But we also prototype on the Chinese machine. So this is what an astronomer would look like. So we want to do things like scatter by day, copy the measurement sets, move them, split them, do some ephemeral processing, do phase rotation, try and predict what the sky model will look like, because we roughly know what the sky looks like. We'll try and subtract that, and it's the bit that we didn't see that's interesting, and we'll use that. So each of these effectively is parallelize, 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 and then we have group bys to bring it all back together again. And we try and avoid them as much as possible. JavaScript.
Okay. And B, ephemeral spelled wrong.
Oh yeah, that's because Chen is Chinese. Oh. So, let's have a look at what an execution looks like across, this is 500 compute nodes on TIN2. Our compute node is 36 cores. We have a whole system. It's based on what we call drops, which doesn't stand for anything. We're thinking of, Andreas was thinking of words that might sort of work, and drops one he liked. And we then run it. And you can see as the patterns start to appear, as the data moves, so we're trying to minimize data movement between each of the nodes. And we can use the Deluging engine to do that as well, because moving data is a bad thing. It takes time. Time is the one commodity that is ultra precious to us. But you'll also notice, timing was bad. Here, we see quite a few red nodes occur. They're ones that just failed. We don't know why. So part of the 4,000 drops failed on that run through this thing. So we're also now looking at how we can build some more fault resilience into it. So for important frequencies and channels, we'll say we'll try again somewhere else. I mean, if it's the area that you want, and Sod's law will always kick in at this point, the one that goes wrong is the one that you're actually interested in. We can say these are the important bits, we'll try redoing them. If it's early enough in the chain, we can probably catch it up. If it's far enough down the chain and it fails, nothing we can do, because we've got to go all the way back to the beginning again. We'll just run out of time within that window.
For those areas which are important, would it be worth doing some of them twice, just in case?
Well, begs the question, are you an eccentric billionaire, and can you afford to give us the extra money we need for the computing to be able to do it? That's the killer. We just don't have the computing capacity to do it twice.
I was just thinking for the things which you decide are important.
Yeah, but unfortunately what's important could be a third of the amount of data that we're looking at. All right, so for the last prize for the day, the Aperture arrays are coming to Australia. And of course everything in Australia is bigger than South Africa. So what do you think the data rate in terms of global internet traffic is? And we'll use units of 100, and you can do it with one hand. It's the right answer. It's 100 times the global internet traffic is what we're expecting to go through this thing. Just out in the middle of the bush in Western Australia. And so few people know about what this actually is that we're doing. All right, now, to save me some time later, one of the things that I'm always asked is, where are the aliens? All right, so let's just re-emphasize again on the sheer scale of space. Now remember that number I told you about the zetaliters of water. Now this is from Jill Tarter, who's the ex-head of the SETI Institute. If you envisaged our galaxy as the oceans of the planet, what we've surveyed so far is about 350 milliliters. So that's a midi and a couple of shot glasses. That's all. We've only had the technology to be able to do this for the last 4 years. We've had radio telescopes, yes, but we couldn't see that far with them because they weren't sensitive enough. We have to remember, our galaxy is about 100,000 light years across, and we're not actually that big. M87 is 980,000 light years across. That's a big boy. We're looking at somewhere between 100 and 400 billion stars in our own galaxy. I mean, the oldest star we found is about 13.7 billion years. So we've been around for a long, long time. Now, the other thing we have is the Drake equation. Now, this was, again, invented the year I was born. A lot of good things came out in 1961, and Drake's equation was one of them. So some of these we actually know now. The star formation rate within our galaxy, we know. We've measured it. It's about 7 stars a year light up. The fraction of those stars that have planets has been a pleasant surprise. The Kepler mission has shown, it turns out, most of them have planets. Now we can then look at sort of an optimistic or pessimistic view on it. I prefer the optimistic one. Number of Earth-like planets, a couple. Number of habitable ones, maybe say 50. Fraction of those that where life exists, that intelligence develops. Now this is a key thing. Dolphins are intelligent. We know this, we've studied them. In fact, dolphins might be more intelligent than us, in that dolphins have learnt to respond to 50 of our words. To my knowledge, nobody has learnt dolphinese. So we can't talk back. But they've never developed technology because they're marine-based. It's very difficult to forge steel sub-sea. Well, there's that too. It doesn't help, but octopus.
Well, they use tools.
No problem at all. But again, it's that ability to develop technology that we can't do. So we then have, of those, how many actually get to technology? Well, lifetime of high-tech communications. Well, we could be optimistic, you know, that's us. We're only about 100 years old. And for the more venerable members of the room who remember the Cold War, we might not have got there. I mean, the Cuban Missile Crisis. Both hands were poised above the button. Ronald Reagan. I mean, we've now got an equally idiotic person in charge of the American button, but we could only think, you know, that's us at the moment. You know, that would be nice if we can get there. So put those numbers in. If we look at the optimistic, there's about 2,000 galaxy civilizations that could be out there. But when you look at the volume, it means the nearest one is about 1,800 light years away. Well, what were we doing 1,800 years ago? Yeah, you know, I mean, if they looked at us, those of us from the Northern Hemisphere, well, basically, we were living in houses that were made of weaved wood covered in cow shit, which was called wattle and daub. And that's what our houses were. It is, you know, change the name from cow shit to daub and leave it to dry. So really, when it comes to it, you know, we haven't been looking long enough. Now, with the SKA, once we get that going, our ocean analogy will start to be swimming pools. Now, it's a bit like looking for fish in the sea. Now, if you put a midi glass into the water and said, oh, there's no fish in there, do you then say there are no fish in the sea? Once we start to get to Olympic-sized swimming pools and orders of magnitude of Olympic, side effects of this is we've built an instrument that can actually, we've invented passive radar. You know how when radar-guided missiles lock onto a target, the target knows it's been tracked and it will screech to release the countermeasures. We can see planes that are reflecting cell phones. Oh, it's gone red. So, what has astronomy given back to it? Well, you saw the images I showed earlier of MRIs and PET scans. All of that imaging technology came from us. The amazingly accurate clocks that you were asking about earlier that work and drive GPS, they're based on hydrogen masers and atomic clocks and cesium clocks, who were invented by radio astronomers. Notice any similarities? Oh yeah, if you took Parkes and shrunk it down, there's where we have satellite telly. And of course, I mean, I don't need to ask you guys, you know where that was invented. But you'd be surprised how often I have to explain to people, if an Australian asks you where was Wi-Fi invented, there's generally a good indication it was here, not the bloody USA. You know, this is invented here. So, finally, to wrap it all up. Now, go back. As children, we all live in this world of fantasy and imagination. Some of us never grow up. That's my job. Thank you. Anybody any questions? Let me just put my secondary hearing aids on.
It's more of a minor question, but are there many like notable radio telescopes in Tasmania? Because I think I've played with one. Is it near Hobart? Yeah.
We very long baseline interferometry, which is one of the techniques I was talking about, where we can really get the angular resolution down, because we're not talking tens of kilometres or hundreds, we're talking thousands of kilometres. All of that was pioneered at Curtin. So again, hey, West Australia, we're good at this. Yes?
So what will be the first targets for this array when it will be up for everyone?
There are 10 science cases that are driving the telescope. The epoch of reionization is one of the biggest, which actually none of the numbers there cover that one. That is completely separate to those numbers, because that one's really quite hard to do. What we're looking at there is basically when stars started to turn on and galaxies started to form. But the redshifts that are involved in that are actually really quite large, and the volumes of data are enormous. But we don't need to do a huge amount of the other processing we do. So we'll have that as a separate pipeline to be able to just look for that one. We want to look for cosmic magnetism, something you can't study at all in optical. We can see it. How the polarization of the radio waves changes by the magnetism. Pulsars. Again, we'll be using pulsars to start looking for gravity waves. Pulsars are neutron stars, so imagine taking our sun and compress it down to about 25 kilometers across. Same mass, but only 25 kilometers across. And give it some angular momentum, and it will generate a regular timing signal. Bing, 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 bing. And we can use that as a marker for looking for gravity waves. If we suddenly see a subtle change in that, what happened? Did something go through there? Did space-time change as that ripple went through? What other ones are there? There's just general survey. So look up, watch the world go by. So what's called drift scanning. The folks again at Curtin have pioneered this technique, and go and look at ICRA's Facebook page. There is the best image of the galactic core ever produced was done by Natasha there a few weeks back. And it's absolutely stunning. And there's a little red dot in the middle of it. Anyone want to make a guess what the little red dot is? No? If you know that the frequencies were things like 96.4, 97.7, 92.5 megahertz, any idea? It's the moon. It's reflecting FM. It's the moon reflecting FM radio. But we see it as a super loud signal. Even after it's been all the way there and that array can see cell phones in Perth. And that's one of the things that James has given me some data for, so we can try and get rid of and see if we can mark out the trains that go past the Murchison at 100 kilometres away. We still probably can see them, but we can see the RFI and flag it and remove it from that type of thing. So it's all fun stuff. Any other questions?
You talked about getting the timings across the arrays by having a delay. But could you also pick up multiple angles simultaneously?
Oh, we do. Because we know exactly at the time, we can do what's called beamforming. So because a dish points at a time, that's all we can see. The low frequency is just a load of antennas. So we can form beams looking that way, and that way, all at the same time. Pi. Yeah, basically it's, I mean, it's just beamforming. I say just beamforming, I mean, the maths is quite scary. And there's a number of sort of new techniques that are coming out to improve how we do that. But it does give us that capability to be able to look in multiple directions at the same time.
So is the correlator on the science the delay to get the individual beams?
The correlator is up at the Murchison, yes, and all of that information feeds back into that to do that. But the beamforming is actually moved for the MWA is a separate box that's actually out next to each of the tiles. And then it comes back to the correlator. For ASCAP, because it's dishes, it's a bit easier, it's pointed over there. Well, it can only be over there.
The various angles you want at the correlator, not later in the process.
No, if you can keep the voltages and all the way through, you can then reform it. Because all we've done at the correlator is say this has seen this at this point. Because it doesn't matter which way the wave's coming in.
Banks of tiles, not just one set of tiles.
Yeah.
Does the data processing pipeline at something like CERN provide a model, or does the continuous nature of your processing make it totally different?
Ours tends to be a little bit, ours is a bit harder because it has to be pseudo real time to be able to do it. Now, all they're doing at CERN is dump data, dump data, dump data. And then 6 months later, they'll come back and say, yeah, look, we found it. But they've recorded all the data. Now, great example, because a room full of IT people, when they were first speccing the Atlas detector at CERN, they said, we will be storing to disk 1.5 terabytes. Last year, they put 42 petabytes of data down. We really are good at this underestimating, aren't we? Yes. At the end of the day is how you get past that bloody red pen. By these things tend to expand though to fill the available space. This telescope is fairly unique in that it's also planned the archive as part of the system. Usually they're just bolted on as an afterthought. MWA is a bit like that. ASCAP, when they first spec'd ASCAP, it was 2 500 gig drives. How the hell are you going to be doing terabytes of data onto that? So they had to add it in. But this, we've actually spec'd it from the very beginning. There will be an archive and there will be regional centres. There's been a certain amount of politicking going on because the regional centres are something that we want to see certain countries take up and run and fund themselves. We're working to make sure there's one here. Here. Not just Australia. Here, Perth. No, because it'd have to be probably down somewhere like Kwinana because of the power. I mean, when you've got that amount of power, the transmission costs and the losses shipping it across Perth could be quite large. But that's why the desalination is next to where the main power is. We would probably be the same because, the truth be told, Telhen 2 is 24 megawatts. Somewhere I think is 18 megawatts. That's a lot of power. I think Western Power reckoned that a typical Perth suburb uses about 1 megawatt. So that's a lot of power. So if you live in the southern suburbs, in a few years' time and your air conditioning won't start, you've got my apologies in early, all right? It was us, sorry, we turned the computers on and we sucked all the power out of Western Power. So, I mean, that's, again, another set of big problems we have to deal with, all this infrastructure. Murchison, there's 1 megawatt of solar out there. Bless Elon Musk. Those power walls might actually be useful for us because we're using diesel at night. Well, with 1 megawatt of daytime solar, we could fill these bloody batteries up and then keep going overnight. So this type of technology may well be sensible. And you think, how many people have got solar panels on their roofs? Yeah, most of us. If they'd have kept that going and we had the ability to store, we could power that just off residue and the sort of oversubscribing from people's solar. We'd have been able to pay for it without, but is any politician going to have the gumption to step up and say, yep, we'll keep on funding that because it's good for Perth and it's good for our environment? Nah, of course they're not. Don't be daft. Any other questions?
Are you hiring?
We're always looking for people to work with us. Now, we actually will pay contract rates as well. We just finished working with Think Bottom Up, who do a very clever database that will eventually synchronize, so we can have it distributed across umpteen nodes and use it for metadata storage. It will finally, ultimately become consistent. We work with Amazon, which is where James and I knew it, in his past life before he went to the evil empire. He actually was...
No, he's not working for Microsoft at all.
No, but he's a coming contractor. Working for an organisation that's more interested in the money than... we work with... But Amazon have given us an absolute fortune to get this through. And one of the things we would love to see is Amazon moving a presence here in Perth. Which question? His question.
Have you tried their FPGAs?
Not yet, but we will be. One of the things that I'm looking at doing, a list of things a mile long, and this is why, why we are quite happy to, if people want to come and do work with us, we're always happy to take on volunteers, and there's a good business case and you've got some skills that we really need, we do look to hire. I mean, we've just hired a position that's joint us and CSIRO, and I need somebody who can compile and beat the living bejesus out of the bloody Cray, because, Intel have a great compiler, GC is a great compiler, but sodding Cray have their own. And stand on one leg, put one hand on your head, rub your tummy 3 times, turn around going la 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 la, and it might compile. I mean, the code that I have the least problem with is Fortran 77 that was written years ago. That works. This modern stuff, MPI, anything to do with huge parallelization, big data storage, all of these types of things. Now, things like big data analytics, our data is big, but it's not the classic big data where you have thousands of different types. It's just big. And it has maybe 15 columns. Billions of rows per day. So it's a different thing. But yes, we're always looking, and there's me. So we're always interested to talk to people. I'm chatting to a student from Murdoch tomorrow who wants to come. He's the type of student we want, not the one who's going to go and make a website that goes, yeah, he wants a tough problem. Silly sod. Fancy coming to me for that. We have real tough problems for things. So, I mean, if you've got sort of connections into universities and students, we work with any university, because ICRA is a joint funded body, so we're funded by UWA, Curtin, and the state government. So we'll quite happily work with Murdoch and ECU and Notre Dame, Swinburne, who else have we worked with? ANU, etc. There aren't many places where you can deal with this type of problem. This is a once in 50-year project. I'm 55. I'm not waiting for another one. I won't be here. That's why I moved out of industry in 2009 to do this project, because I looked at it and thought, I ain't going to be able to do another one because there won't be another one in Australia. Time to take a 60% pay cut and move into academia. And I wish I'd done it years ago, actually. I mean, this is normal working clothes, apart from I'm actually wearing shoes at the moment, which I don't normally wear. But it's cold outside, so... and the corporate branding, because I'm on camera. Well, no, I'm on camera, so corporate branding, we have to have to do the right thing, because Cooper's, Lie Brown, what's his name, Whitehouse and Dudar, the Deloitte thingy-abobs, the accountants are auditing at the moment. Now, last time they came through, they looked at the 20 million the state government had put into us and estimated that we had bought in $106 million worth of, so that's a pretty good investment for the state. And they're now doing the secondary audit, or another one to see where we are. And ICRA was formed in 2009. We're now about the 5th most prodigious astronomy institute on the planet. And we're here in WA.
Is the state sponsoring anything now, or is it all just federal?
No, the state is still, the state sponsors ICRA. The federal government is actually just the data intensive folk. You know, we need to finish this design. We've got to work out how we tender this so that people can actually bid sensibly, and it can also go to smaller companies within the host organizations, and we're not going to see the likes of Agilon and IBM Global Services and HP just say, yeah, we'll do that, just give us the money. We want to see the smaller people involved, because actually a lot of the smaller people still remember how to think. And that's actually important. You may laugh, but the corporate structure doesn't encourage that. We like you to think outside the box, because it may be, well, that's actually a damn good idea. Why didn't nobody ever thought of that? And that's why I do a lot of work with kids. And that's great fun, because NASA did a test for engineers, of which only 5% of engineers would pass. But if you give it to pre-11-year-olds, 40% would pass, because they haven't been taught. Well, here's a standard student, here's a standard computer program, here's a standard Java name, a standard C++ name. Actually, we need people who can really think outside the box, because the problems are really very tough. And you have to be able to sort of work independently and freely and just get on and do it. And it's also nice to get some results back. You know, we don't tend to look too much. What's the name of the guy? He wrote a paper in 1936, The Usefulness of Useless Knowledge. And it became sort of the main theme of Johns Hopkins and their research philosophy. And I think it's Purdue University, where you are a researcher. Do research, because I'm not going to be sitting and looking over you, shoulder. Get on and do it. But try and get something that's useful come out of it. You know, patents are always good. Any other questions? No? Now, if anybody's got any kids who are interested in spacey things, I've got some planar spheres, so you can find your way around the sky. Really idiot-proof. They even have the instructions on the back, so you can give it to your kids. They're here, and a few pens as well, if you're interested in pens. Those of you who want the mugs, don't put the mugs in dishwashers. Right? I mean, it says it on the box, it says it inside, and I've also now told don't put them in dishwashers, because the dishwasher will strip away the funny colour and stuff that shows you the pretty picture.
And what does the microwave do?
Whoa!
Don't use it in the microwave either.
The microwave causes it to very slowly explode.
Very slow explosion. Right.
Yeah. Someone must have microwave mine. It's fine as a crack in it.
Ah.
Yeah.
It feels in the whole galaxy with microwave radiation.
There you go.
Just throw it on there.
Oh.
See? Failures happen all over the place, don't they?
Always carry spares. No,
I'm
I'm speaking in Pinjara to 50-year 10s tomorrow morning. So one of them's not going to get a mug.
You just talked a year 10 of
That year 10.
It's okay. I have it special for them, you see. They can have it. ruler that shows
but
the
what if-
evolution from the Big Bang.
What if that was that year 10 student that I deprived this mug of? It was like the person who was gonna like make a breakthrough.
You can have the hat. And the t-shirts. You see, you guys don't actually get the original. The whole of the thing. So we have a whole grab bag of goodies that we give out. So you don't need to worry about it.
Thank you very much.
My pleasure.